In computing, the modulo operation finds the remainder of division of one number by another. Given two positive numbers, a and n, a modulo n is the remainder of the Euclidean division of a by n. For instance, the expression 5 mod 2 would evaluate to 1 because 5 divided by 2 leaves a quotient of 2 and a remainder of 1, while 9 mod 3 would evaluate to 0 because the division of 9 by 3 has a quotient of 3 and leaves a remainder of 0. There is nothing to subtract from 9 after multiplying 3 times 3. Although typically performed with a and n both being integers, many computing systems allow other types of numeric operands. The range of numbers for an integer modulo of n is 0 to na1. See modular arithmetic for an older and related convention applied in number theory. When either a or n is negative, the naive definition breaks down and programming languages differ in how these values are defined. Remainder calculation for the modulo operation. In mathematics, the result of the modulo operation is the remainder of the Euclidean division. However, other conventions are possible. Computers and calculators have various ways of storing and representing numbers. Thus their definition of the modulo operation depends on the programming language and/or the underlying hardware. In nearly all computing systems, the quotient q and the remainder are satisfy. This means that, if the remainder is non-zero, there are two possible choices for the remainder, one negative and the other positive, and there are also two possible choices for the quotient. Usually, in number theory, the positive remainder is always chosen, but programming languages choose depending on the language and the signs of a and n. 5. Pascal and Algol 68 give a positive remainder even for negative divisors, and some programming languages, such as C89, don't even define a result if either of n or a is negative. See the table for details. A modulo 0 is undefined in the majority of systems, although some do define it to be a. Many implementations use truncated division where the quotient is defined by truncation q equals trunc, an, in other words it is the first integer in the direction of 0 from the exact rational quotient, and the remainder by r equals aanq. Informally speaking, the quotient is rounded towards 0, and the remainder therefore has the same sign as the dividend. Knuth described flawed division where the quotient is defined by the floor function q equals floor, an, and the remainder r is. Here the quotient is always rounded downwards and the remainder has the same sign as the divisor. Raymond T. Boot introduces the Euclidean definition, which is the one in which the remainder is always positive or 0, and is therefore consistent with the division algorithm. This definition is marked as always positive in the table. Let q be the integer quotient of a and n, then. Two corollaries are that. Or, equivalently. As described by Leijen, Boot argues that Euclidean division is superior to the other ones in terms of regularity and useful mathematical properties, although flawed division, promoted by Knuth, is also a good definition. Despite its widespread use, truncated division is shown to be inferior to the other definitions. Common Lisp also defines round and ceiling division where the quotient is given by q equals round, an, q equals ceil, an. IEEE 754 defines a remainder function where the quotient is an rounded according to the round nearest convention. Common pitfalls. When the result of a modulo operation has the sign of the dividend, it can sometimes lead to surprising mistakes. For example, to test whether an integer is odd, one might be inclined to test whether the remainder by 2 is equal to 1. But in a language where modulo has the sign of the dividend, that is incorrect, because when n is negative and odd, now %2 returns a 1, and the function returns false. One correct alternative is to test that it is not 0. Or, by understanding in the first place that for any odd number, the modulo remainder may be either 1 or a 1. Modulo operation expression. Some calculators have a mod function button, and many programming languages have a mod function or similar, expressed as mod, n, for example. Some also support expressions that use %, or mod as a modulo or remainder operator, such as, or %n, or, a mod n, or equivalent, for environments lacking a mod function, a. Performance issues. Modulo operations might be implemented such that a division with a remainder is calculated each time. For special cases, there are faster alternatives on some hardware. For example, the modulo of powers of 2 can alternatively be expressed as a bitewise AND operation, $2 and x and. Examples, $2x and 1, $4x and 3, $8x and 7. In devices and software that implement bitewise operations more efficiently than modulo, these alternative forms can result in faster calculations. Optimizing compilers may recognize expressions of the form expression a %constant where constant is a power of 2 and automatically implement them as expression AND. This can allow the programmer to write clearer code without compromising performance, because if the dividend is negative, the modulo will be negative. However, expression AND will always produce a positive result. So special treatment has to be made when the dividend can be negative. Equivalences. Some modulo operations can be factored or expanded similar to other mathematical operations. This may be useful in cryptography proofs, such as the Diffie-Hellman key exchange. Identity. For all positive integer values of if is a prime number which is not a divisor of, then, due to Fermat's little theorem. Inverse. Denotes the modular multiplicative inverse, which is defined if and only if and are relatively prime, which is the case when the left-hand side is defined. Distributive. Division, when the right-hand side is defined. Not defined otherwise. Inverse multiplication, see also, modulo and modulo are many uses of the word modulo, all of which grew out of Carl F. Gauss's introduction of modular arithmetic in 1801. Modular exponentiation, notes, Perl usually uses arithmetic modulo operator that is machine independent. See the Perl documentation for exceptions and examples. Mathematically, these two choices are but two of the infinite number of choices available for the inequality satisfied by a remainder. Divisor must be positive, otherwise not defined. As implemented in AccuCOBOL, Microfocus COBOL, and possibly others. References: open-std.org, Section 6.5.5, ISO IEC 14882-2003. Programming languages, C++ 5.6.4, ISO, IEC 2003a. The binomial percent operator yields the remainder from the division of the first expression by the second. If both operands are non-negative, then the remainder is non-negative. If not, the sign of the remainder is implementation defined. Expressions. Deprogramming Language 2.0. Digital Mars. Retrieved July 29, 2010 abr6rs.org, Newth, Donald. E. The Art of Computer Programming. Addison Wesley, Boot, Raymond T. The Euclidean Definition of the Functions Div and Mod. ACM Transactions on Programming Languages and Systems, 14, 127 144 doi, 10.1145/128861.12886 Lenigen, Dan. Division and Modulus for Computer Scientists. Retrieved August 27, 2006. Horvath, Adam. Faster Division and Modulo Operation, The Power of 2a.